In this lesson, we are going to continue with the symbolic math. So let's first take a look at how do we perform differentiation with symbolic math. So say we define our symbolic objects of x, y, and t, and we have an expression s is equal to the exponent of x to the power of 4. So if we want to calculate the differentiation of this equation here, we can simply use the command diff of s, and when we press enter, we get 4 times x to the power of 3 times exponent x to the power of 4. We can also differentiate twice the expression by typing in diff of s, comma 2. This will produce the second differentiation, the second derivative of s. When we press enter, we see that this expression here has been differentiated one more time to obtain 12 times x to the power of 2 times exponent of x to the power of 4 plus 16x to the power of 6 times exponent of x to the power of 4. We can also type the equation directly within the differentiation command. For example, we type in diff of 1 minus 4 times x to the power of 3. When we press enter, we get the differentiation of this equation here that we type in directly. Say that we have two symbolic objects, y and t, and we define the equation R that is equal to 5 times y to the power of 2 times cos of 3 times t. This is our expression, and if we simply perform diff of R, MATLAB will differentiate the equation here with respect to y, because MATLAB has automatically select y as the default variable. In the case if we would like to differentiate with respect to t, we can type in diff of r comma t. This will give an answer of a differentiation of this equation here with respect to t. We can also perform integration using symbolic math. For example, we have x, y, and t as the symbolic objects, and we have an equation of 2 times cos of x minus 6 times x. And if we want to integrate the expression s, we can simply use the command int in bracket s, and we will get the integration of this term up here. So 2 cos x minus 6x, integrate becomes 2 sin x minus 3x squared. We can also type in the expression directly in the bracket. For example, integration of x times sine of x. When we press enter, we get the integration of this term here. And we can also, for example, if there are more than one variable, let's say we have an expression of r equals to 5 times y to the power of 2 times cos of 4 times t. And if we do int of r, we will get the integration of this term with respect to y. If we would like to integrate with respect to t, we simply type in int of r comma t. And we can also include the definite integration by including the lower and upper range. For example, if let's say we have an expression a that is equal to cos of x, for example. So if we integrate a, we will get sine of x, and we can also perform integrate of a comma the range if we would like to get the definite value of the integration. So let's say the range is from 0 until pi. So this is the command that we should type in: integration of a comma lower range comma pi the upper range. So if we press enter, we get the answer as equal to 0. Let's look at another example. Let's say we have another expression b that is equal to sine of y minus 5 times y to the power of 2. This is our expression. So if we would like to integrate this expression, integrate of b, comma, the lower range is 0 until pi. When we press enter, we get the value of this definite integration that is equal to 2 minus 5 times pi to the power of 3 divided by 3. And if we would like to get the approximated value of this, we can always use the double command, double of answer, then we get the approximated value of minus 49.6771. In the previous lesson, we have discussed how to solve algebraic equation and also simultaneous algebraic equation. Symbolic maths can also be used to solve differential equation. Let's take a look at how we solve this differential equation here. We have dy dt equals to 4t plus 2y. In symbolic maths, the default variable, the default independent variable is t. So in this case, what we need to do to solve this differential equation is first to define the symbolic object sims of y in terms of t. Y is the dependent variable that is depending on t. T can be anything like time, for example. So when we press enter, you will see that two symbolic objects appear in the workspace. The first one is t, which is a symbolic object, and y appears as a symfun, which is a symbolic function. Now, to solve this equation 4t plus 2y, we first define that we define dy is equal to diff of y. So basically, dy is equivalent to the differentiation of y with respect to t. So in other words, we are saying that dy is equal to dy over dt. So we can put semicolon here and press enter. And to calculate to solve the differential equation, we can use the command dsolve, d for differential and solve to solve the differential equation. That is equal to dy, our equation here. Dy is the differentiation, dy means dy over dt. We put double equal here, which means that it is equal. So dy here, capital D and y represents dy over dt, because we have defined up here that dy is equal to the differentiation of y, which is equivalent to dy dt, and this is equal to 40 plus 2y. So here we type in 4 times t plus 2 times y. So when we press enter, MATLAB will give us an answer C1 times the exponent of 2 times t minus 2t minus 1. Okay. We can also calculate the second order ordinary differential equation, and in this case we define d2y, which indicates the second order differentiation, that is equivalent to diff of y comma 2. Remember in previous lesson we say that comma 2 here means the second derivative of y. So we can press enter here. Now d2y appears as another sim function. So now we would like to solve this equation here, d2x over dt square plus d2 plus 2 dx dt plus x is equal to 0. In this case we say d2y. It is actually the same thing. We can also change to y if we want, but let's we can change to x if we want, but let's just stick to y in this case. So we're going to type in d2y plus 2 dy plus y is equal to 0. So that is the equation that we would like to solve. So now let's type in dsolve d2y plus 2 times dy plus y is equal to 0. That is our equation here. Let's take a look at the equation again. So we have d2x dt. In this case we type in as d2y plus 2 times dx dt. We have here plus 2 times dy, and plus x, we replace x with y, so plus y is equal to 0. So that is our equation. So when we press enter, we will get the answer C4 times exponent of minus t plus C5 times t times the exponent of t. Now let's take a look at how can we solve this differential equation. We have ds dt equal to ax square. So now we need to define our symbolic objects. We have s in terms of t, we have a, we have x. So we define ds, that is equal to the differentiation of our equation s. Okay, and then to type in this equation, we simply use dsolve command, dsolve of ds equal to ax square. So we type in dsolve of ds, that is equal to a times x to the power of 2. When we press enter, we will get the answer of a times t times x square plus c constant. So we can see here that the differentiation or the solution of this is calculated with respect to the independent variable of t. That's why nothing has changed. Ax square here has not been changed, but the variable t has been added to the solution, because MATLAB has calculated the solution with respect to the variable t. Now, if we, let's say, want to solve this with respect to x, we can always use the dsolve command, and we type in comma of x. Okay, and when we press enter, now MATLAB will calculate the answer with respect to x, and we got a totally different answer from what we have up here, we have now ax cubed divided by 3 plus the constant. We can also solve with respect to a by replacing this variable x with a. We will get another answer that is equal to a squared times x squared divided by 2 plus the constant. So please remember that if we do not include any variable within the dissolve command, MATLAB will automatically solve the differential equation with respect to t, because it assumes that the independent variable is t. So if, let's say, we want to calculate with respect to any other variables other than t, we have to define it in the dissolve command. So now let's take a look at how can we obtain a particular solution of an ordinary differential equation in MATLAB. And to get a particular solution, the boundary or initial condition must be specified when solving the equation. So let's see how can we solve this first order ODE, dy dt plus 4y equals to 60, and the given initial condition of y0 is equal to 5. So to solve this, first we need to define the symbolic object of, in this case, y with respect to t. Then we also define dy, that is equal to the differentiation of y over t over dt. Then we can use the dissolve command, where here we have dy plus 4 times y equal to 60. This is what we have here. Dy dt is represented by capital dy here, plus 4 times y equals to 60. And we need to include the initial condition of y0 equals to 5 in order to get the particular solution for this ordinary differential equation. So we put a comma here and we say y0 is equal to 5. Remember that we need to use the double equal sign here in both inputs to indicate that this value is actually equal and is not assigned to y0. So when we press enter, we will get the particular solution of this differential equation, that is equal to 15 minus 10 of the exponent of minus 4 times t. We can also solve the second order ODE to get a particular solution as well. In this case, we have d2y over dt square minus 2 dy dt plus 2y equals to 0. And we have two conditions given here, y0 equals to 1 and dy dt at t equals to 0 is equal to 0. So to solve this, we need to define another variable that is d2y. This is then equal to the differentiation of y comma 2. It's the second derivative of y. Then we can enter the equation within the dissolve command. We have here d2y dt square minus 2 dy dt plus 2y. So basically we have d2y minus 2 times dy plus 2 times y is equal to 0. This is our equation here, d2y minus 2 times dy plus 2y equals to 0. And we have two conditions, y0 equals to 1. So we put a comma, y0 equals to 1. And we have another condition, dy 0 is equal, dy dt at t equals to 0 is equal to 0. So we have here comma dy 0 is equal to 0 as well. So we have three inputs here. This is the equation, this is the first condition, this is the second condition given. So when we press enter, we'll get the answer of exponent of t times cos t minus exponent of t times sin t. So that is solving differential equation using symbolic math. Now let's take a look at how can we plot a graph using symbolic math. Just like the plot command for a normal operation, in symbolic mathematics, we can also plot the function. For example, if we do sims of x and we have the equation s is equal to x squared, okay, we can use to plot the function as a symbolic function or symbolic expression. We use the command ezplot instead of the normal plot command. So ezplot, now our function, you see the hint given by MATLAB is ezplot, and in the bracket we need to input the function. So in this case our function is s. So if we do ezplot s, we press enter, we get the plot of x squared. We can plot, for example, more than one graph. Let's say now we have a sims of t. We define t as a symbolic object, and we have x is equal to cos of 2 times t, and y is equal to sine of 4 times t, and we can do ezplot of x comma y. When we press enter, we get the plot of x comma y instead of plot of x against t. If we plot ezplot x only, x will be plotted with respect to t. For example, if we do ezplot of x, now x is plotted against t. So if we want to plot x against y, the command is to type in ezplot x comma y. That is how you can plot using the symbolic math. Now let's see how can we substitute numerical value in a symbolic variable. For example, let's say we define x as a symbolic object, and we have a symbolic expression of s equal to 0.8 times x to the power of 3 plus 4 times the exponent of 0.5 times x. So this is our symbolic expression, and then let's say we differentiate this as d. The differentiation of s is equal to diff of s. We have this, and then now we want to substitute the value of x in this equation as d to be equal to 2, so that we will get a numerical answer. So what we can do is we use the subs command, subs. Now we want to substitute in the expression as d, and we want to substitute the variable of x. So we type in x, and we want x to be equal to 2. So we type in the value. So this will substitute the x in expression of sd with a value of 2. So when we press enter, we get the answer in the exact format. So if we would like to see the approximated answer, then we can use the command double of answer. We'll get 15.0366. We can also substitute a range of values. Let's say, for example, we give a name sdu, for example, is equal to subs of sd. We want to substitute the variable x. Now instead of giving just one value, we want to give a range of values. So we define a vector within square bracket. So let's say it starts from 2 with an increment of 0.5 until 4, for example, and we close the round bracket. When we press enter, we will see the expression, the answer for each of the values given of x written in exact format. So we can type in double of SDU if we want to look at the answer in approximated value. So we have 15.0366, 21.98, and so on and so forth for every value of x that we have substituted in the expression SD. MATLAB will display a separate answer. Let's look at another example. Say we define a few symbolic objects A, G, T, and V, and we have an expression y that is equal to v squared times the exponent of A times T, and then divided by G. So this is our expression, and we want to substitute T now with a value of 2, so we use a common subs. The expression is y, comma, t, comma, 2. So we want to substitute the variable t in the expression y with a value of 2. So when we press enter, we see now v squared times exponent of 2 times a instead of a times t. Now t has become 2, so it becomes 2 times a divided by g. And then we can also substitute a range of values. For example, I give a name yt to the variable equal to subs of y. We want to substitute t with a range from 2 until 4. If we do not define the increment, the increment will automatically be set as 1. When we press enter, we see the expression now written separately for every value of t that we have substituted in the equation of y. So now let's take a look at another example. Say now we have defined a symbolic objects A, B, C, E, and X, and we have an expression of S that is equal to A times X to the power of 2, AX to the power of E plus B times X plus C. So this is our expression, and let's say we want to substitute all of these values, all of these symbolic objects with numerical values. We can also use the subs command, subs of S. The expression is S, and then we have to give we have to define it in a cell array by using the curly bracket. So we say A, comma, B, comma, C, comma, E, comma, X, and comma here, and we do the same within a curly bracket, the respective value of each of this variable. Say A is equal to 5, B is equal to 4, comma, C is minus 20, for example, E is 2, and X is 3. And we close the round bracket. When we press enter, we get a value of 37 because all of these symbolic objects has been replaced with a numerical value. Okay. And there is also another way of doing this, of substituting numerical value into symbolic expression. Let's take a look at this example. Say we define symbolic objects of A, C, M, X, and Y. And we have the expression of S equal to A times cos of M times X plus C times Y. This is our expression. And before we use the subs command, we define the value of each of the symbolic objects first. Let's say we want A to be equal to 10. and we say m is equal to 0.5, and then c is equal to 3. So we define three variables, as we define three numerical values for these objects, the symbolic objects a, m, and c. We press enter, and we simply type in subs of s without defining the variable inside the bracket. So we define the variable before we type in the subs command. So when we press enter, we'll get the answer of 3 times y plus 10 times cos of x over 2. So see that a has been replaced with 10, m has been replaced by 0.5. Here it becomes divided by 2, x is divided by 2, and c has become 3. Here in front, 3 times y is actually the value of c. So there are two methods. Either you substitute all the values inside the subs command, or we can define the value before we type in the subs command. So that is how we substitute numerical value in the symbolic expression.